Okay, so in this video, we're going to talk about complex numbers arguments. So we know that a complex number can be written in this polar form, right? Or some of you might call it the exponential form, where we describe a complex number using its modulus and its argument. And typically, we would draw an Argand diagram to visualize this complex number. So on this Argand diagram, we have a real axis running horizontally and an imaginary axis running vertically. A complex number can be denoted by a point on the Argand diagram. So let's say I have this complex number z, right? Complex number z. And this complex number has a modulus of r, which means it is a distance of r units from the origin. Okay, and the argument, which is theta, is measured. Okay, so the a description of what an argument is over here. So an argument is the angle measured anti-clockwise from the positive real axis to the line segment, or you can call it the position vector, right? Okay, so let me maybe just add it in. You can also say that this is the position vector. Okay, position vector of the complex number, right? From the origin to the point representing the complex number on the Argand plane, right? So in fewer words, it's basically if I have a complex number z that is represented by this point, then if I have a position vector that goes from the origin to the complex number, I can measure the length of this vector, and this is called the modulus. From the positive real axis, if I measure an angle in the anti-clockwise direction, right? Anti-clockwise, from this positive real axis measured to this position vector, this would be the argument. Okay, so what happens if you measure the other way? So let's say I want to measure maybe clockwise instead. Then in that case, this would be a negative angle. So let's say I measure maybe a negative pi over 2. This would be the angle. Okay, so we can measure clockwise, but there will just be a negative angle. Okay, now let's look at an example. So let's say I have a complex number like this, right? Z has a modulus of root 2 and an argument of 5 pi over 6. So let's try to denote this complex number on the Argand diagram. So I have an Argand diagram over here, and I have a complex number with modulus of root 2. That's not so important at this point. What is more important is the argument of 5 pi over 6. It's a positive angle, so we are going to measure from the positive real axis in the anti-clockwise direction, and we are going to measure an angle of plus 5 pi over 6. 5 pi over 6. 5 pi over 6 is just almost pi, with a 1 over 6 gap, kind of, right? So let's say I measure this angle, and that means my position vector is pointing this way, right? Maybe let me just draw it such that the angle is actually touching the position vector. Okay, this means that my position vector from the origin to z, okay, this distance here, which is the modulus, is root 2. Okay, so this is how we represent our complex number on the Argand plane. Okay, now one question. Is there any other choice of argument to describe this complex number, right? Because can I measure, for example, because I mentioned just now that we can measure a negative angle, right? Then for this purpose of representing this complex number, I could have measured this way to here, and I will still describe this position vector pointing in this certain direction, right? So I just need to measure out a root 2 and I'll still describe z. So can z be represented as root 2 e to the power of I minus, okay, this angle. This angle is, if you can tell, this is pi, okay, 180, and then pi over 6. So this is just pi. Okay, let me just write it as pi. Sorry, it's minus pi, and then minus another pi over 6, right, which is just root 2 ei minus 7 pi over 6. Right, so can we describe our complex number z like this? Turns out we can, and in fact there are many choices that we can use to describe our complex numbers. So we can define this, we can actually we can rotate our, or we can measure an angle, let's say plus 5 pi over 6. And what we can do is we can just continue turning. Let's say I just want to, for example, 5 pi over 6, and I want to turn another full round for some reason. So let's say I continue turning after I turn the green color one. I turn one more full round. That's plus 2 pi, right? Plus 2 pi. Plus, because I'm still turning in the anti-clockwise direction, and I turn a full round, which is 2 pi. I end up describing the same complex number, right? I still describe the same direction in a sense. So this green color representation and this orange color representation both describe the complex number z. Okay, I guess in this case, let me just write it as z divided by root 2 because I didn't put the modulus there. But yeah, it still describes the complex number z, just without the length of root 2. Okay, what else? Right, if I can turn one full round, can I turn 2 full rounds? Turns out I can. Can I turn 3 full rounds? Turns out I also can. So I can turn a bunch of 2 pi's, a bunch of full rounds, in the positive direction, or I could have turned in the opposite direction. Let's say I turn the green color arrow, right, the green color angle, and I turn an extra full round following the orange color angle. I can then turn backwards, okay, undo the orange color angle, and I will end up in the green color angle. Okay, so I can continue turning backwards again, and I'll still describe the same complex number. So it turns out that we can add or subtract, okay, basically turn anti-clockwise or clockwise, a bunch of 2 pi, so 2 pi times n, or 2n pi. Okay, so we can turn a bunch of full rounds. Okay, so what this means is just turn a bunch of full rounds, or full 2 pi's, I guess. Okay, you can turn clockwise or anti-clockwise. Okay, so it doesn't really matter, right? Clockwise or anti-clockwise. So there are many choices of arguments to describe the same complex number. But because we have so many different choices, and in fact there are infinitely many choices, how do we decide what we should write? Because we probably don't want to write maybe 5 pi over 6 plus 2 million pi's, you can turn a bunch of times. But why would we do that? So what's an accepted way to describe our complex numbers? So what argument should we use to present our answers? We want to follow a certain convention, and this convention is called the principal argument. So it is a convention. Everyone agrees that we will do this. This is the nicest way to write our arguments. So we gave it a name, principal argument. Okay, so principal argument is basically an argument, an angle, measured from the positive real axis in the anti-clockwise direction. So anti-clockwise will be plus some angle. If you turn clockwise, also can, but it's minus the angle. Okay, and the principal argument runs from negative why did I write infinity? Negative pi, my bad. Negative pi to positive pi. Okay, and negative pi is excluding the negative pi. So up till here, okay, and including here. Okay, it looks kind of weird there, but we will just accept that the interval is excluding negative pi, including positive pi. So this is the principal range, right? All right. So knowing this, let's see how we can write our complex numbers using our principal argument, or using its principal argument. Let's find the principal argument of this complex number, right? The easiest way to find the principal argument of a complex number is always to first draw an Argand diagram. This complex number has a modulus of 5. That's not very important yet. This, actually not yet, but in this case, in this question, it's not important, right? We just acknowledge that it's there. The argument that we are given is 5 pi over 3. 5 pi over 3, if you want to, convert it into let's say a mixed number, I guess. Okay, this is just 1 full pi, okay, and 2/3 pi. Okay, I think this seems a bit weird, so I'm just gonna write it as pi plus 2/3 pi. Okay, this will be a bit easier, right, for us to visualize. We are going to start measuring from the positive real axis, and what I'm going to do is I'm just going to draw an arrow. Okay, an arrow. So this is going to be my position vector of the complex number z. I'm going to start measuring from the positive real axis. I'm going to measure positive pi, which is half a round, and then plus 2/3 pi. So this is another pi, but I'm going to only measure 2/3, so somewhere around here. Okay, so let's pretend, right, so it's not really aligned. Let's pretend that this modulus is 5, okay, which is given, and the argument is pi, okay, pi. So let me just break it into two parts. So plus pi, then I plus 2/3 of pi, 2 pi over 3. So this is my complex number. The complex number z is over here. Okay, the complex number z is over here. Alright. Now, what is the principal argument of this complex number? So remember that our principal argument is within this range. You can either turn a positive pi or minus pi, okay, excluding minus pi itself. This angle is too big, right? Too big. So how can we measure a principal argument? Our principal argument, okay, is just this. Okay, we are allowed to turn in the clockwise direction up to negative pi, right? We are also allowed to turn up to positive pi. But when I turn positive pi, I don't find my complex number here, so that's not the way to do it. And when I turn a negative angle, okay, basically clockwise, I meet my position vector of the complex number. So this, whatever angle this is, okay, which in this case is minus of an angle, a negative angle, right? This will be my principal argument. And we can tell that this is pi, this is also pi. If this green color part is 2 pi over 3, or 2/3 of pi, then this angle, the size would be 1/3 of pi. But because we measured clockwise in the negative direction, so this is pi over 3, but with a negative sign. Which means the principal argument of this complex number, the answer is negative pi over 3. Some people like to denote principal argument using a capital A. That's fine. So it is up to whether your teacher likes to do this or not, but let's just use capital A to denote principal argument. Okay, principal argument. Okay, so the principal argument of this complex number is negative pi over 3. Let's look at one more example. So example 3, I have this complex number w, but the modulus is 1. We don't really need to deal with that. But our argument is crazy big, right? It's 101 over 3 pi. Let's write it in a different way again, right? Let's write it as e to the I. Let's see how many full pi's are there, right? The biggest multiple of 3 that is less than 101, well, 101 is not a multiple of 3. So the biggest one is 99, right? So this is like 99 plus 2 over 3 pi. And 99 over 3, that's just 33. So I have 33 pi plus 2 over 3 pi. Okay, 33 pi plus 2 over 3 pi. What that means is, from the origin, I have a position vector that goes to my complex number w. I'm going to measure from the positive real axis. I'm going to measure anti-clockwise an angle of 33 pi. So I'm going to do 1, 2, 3, 4 until 1, 2, 3, 4, whatever, so on and so forth, until I have 29, 30, 31, 32, 33. Okay, so 33 pi should be a bunch of times, like just spiral until I reach here. This is 33 pi. Okay, 33 pi. Okay, now 33 pi, afterwards I'm going to rotate another 2 pi over 3. So I'm going to rotate not one full pi, but 1/3, 2/3 pi. So let's say something around here. So this extra 2/3, okay, maybe I write it in blue. So this extra 2/3 is actually this extra angle here. Okay, 2/3 pi. Okay, and well, notice that the 33 pi is quite difficult to count. I don't want to go and draw like 16 rounds, right? So how can I make this a bit easier to deal with, right? So instead of doing this pretty dumb thing where I just draw a spiral, luckily I didn't draw like all 33 pi, I just put a dot dot dot. But how can I deal with this, right? If I'm given like such an ugly argument, which is quite a big number of pi, what I can do is I can find out how many 2 pi's are within this 101 over 3. I have 33 full pi's and then 2/3, right? This is the same as saying I have 32 plus 1 plus 2/3 pi, right? This is the same as e to the I 1 plus 2/3 pi. This describes the same complex number because I don't really care about the whole 32 pi's. The 32 pi's basically tell me 1 pi, 2 pi, same, it's like angle of 0 again. 1 pi, 2 pi, argument of 0. 1 pi, 2 pi, argument of 0. So 32 pi is essentially doing nothing, right? So I'm just left with 1 plus 2/3 pi, which means instead of drawing this whole spiral of like green color arrows, what I could have done is I just reduced it to 1 pi, okay, so plus pi, and then plus another 2/3 pi. Sorry, I should have written this pi outside like this. 1 plus 2/3 pi. Now this 1 plus 2/3 pi is kind of the same as an example we did earlier on, the one with 5 over 3 pi. So the idea is that I have an angle that is bigger than positive pi, right? Because our principal range goes from positive real axis measured anti-clockwise plus pi, or clockwise negative pi, not including negative pi. So this angle is too big, right? Turns almost one full round. So our principal argument would be to turn the other way. So from your positive real axis, I turn clockwise, but only this angle. Okay, and this will be a size of pi over 3, but it's in the negative direction, so negative pi over 3. Which means I can write my complex number as e to the I minus pi over 3. Okay, or you can put a negative sign outside if you want, doesn't matter. Right? So this is my complex number, but the question asks for principal argument. So principal argument is, let's denote it as capital A argument of W in this case. This is negative pi over 3. And we are done. So that's all for this video.